So we'll start off with structural diagrams for these guys. The structural diagrams I think are easier to draw, and so we usually begin with those. So we're going to look at an example of CH4. When I go to do these, I need to remember the pattern on the periodic table. The first thing I ask myself is, how many bonds does each element make? When I look at the periodic table, it gives away how many bonds each of the elements make. So again, the pattern goes like this. The noble gases have 8 valence electrons, and so therefore they make 0 bonds. I look at the halogens. They have 7 valence electrons, which is shown with the group 7A. They need 1 more electron, so they make 1 bond. The oxygen family has 6 valence electrons. They need 2 more, so they make 2 bonds. Nitrogen has 5 valence electrons. It needs 3 more. It makes 3 bonds. And carbon has 4 valence electrons. It needs 4 bonds. So basically, you take the difference of 8, which is what they want. You subtract how many valence electrons they have. In the case of carbon, it's 4. And you get the number of bonds that it makes. So for carbon makes four bonds. Hydrogen, which is on the other end of the table, makes 1 bond. So the next thing I ask myself is, which element should go in the center? The answer to that question is the element making the most bonds goes in the center. Since that element's carbon, it'll go in the center in this case. So I go to draw it, and I write in carbon. Carbon makes 4 bonds. And so I draw the bonds as lines. And remember, each of those lines equals 2 valence electrons. Each line equals 2 electrons. So I've got my 4 bonds for carbon put in there now. The next thing I do is surround it with the other elements. So in that case, I have 4 hydrogens, which is convenient because there's 4 bonds there that carbon makes. And we're going to add in 1, 2, 3, 4. So now I've got my model for CH4. The last thing I do is make sure that the octet rule is satisfied. So in this case, I look at the carbon, and as we look around it, carbon's got 2, 4, 6, 8 electrons. So carbon is definitely satisfying the octet rule. Hydrogens only need 2 electrons, so each of those guys has their 2. And I'm just circling these to show that you don't have to actually draw the circles. So that would be the structural diagram for CH4. Okay, let's look at another example. Okay, here we have phosphorus trifluoride, or PF3. From the trends on the periodic table, we know that phosphorus makes 3 bonds and fluorine makes 1 bond. So I put phosphorus in the center. It makes 3 bonds, and I surround it with fluorines, who each make 1 bond. So I've got that done. Okay, the next thing I do is make sure the octet rule is satisfied. Well, phosphorus has the 2, 4, 6. It needs 2 more to give me 8, so I'll put the 2 dots above the phosphorus. That gives phosphorus 8. If I look at the fluorines, again, I've got 2 in the bond, and then we add in the rest of the electrons, giving them a total of 8. We do the same here. And we end up with our structure for PF3. Okay, so the octet rule is satisfied. Everybody's got the right number of bonds, and this is a good structure. Let's look at this example because it's a little bit different than the other ones we've looked at so far. Here we have N2, which is nitrogen, and you've seen this one in class, but just to remind you, nitrogen, each of those guys makes 3 bonds. So when I write down the 2 nitrogens, you notice I've got 2 N's. They need to make 3 bonds. There's only 2 elements, so those 3 bonds have to go in between the 2 elements. There's nowhere else to put them. A bond has to attach 2 atoms together. So we've got that down. Now we need to satisfy the octet rule because right now each nitrogen has 6 electrons. If I add 2 more in to each side, and we look at this in a little more detail, we'll kind of just circle this so you can see it. This nitrogen has 2, and then the 6 in the middle, remember each line is 2 electrons, for a total of 8. If we look at this guy, he's got the 2 plus the 6 in the middle, which gives us 8. So the octet rule is satisfied for N2. N2 has to triple bond to do that. Okay. In contrast to that one, if we look at F2, which we'll just handwrite in here, for F2, fluorine only makes 1 bond. So we have that. It doesn't need the triple bond to do this. So we go through and we put in the dots for that. Fluorine is single bonded. If we look at O2 though, for O2, we have 2 O's connected. Well, each oxygen, according to the trends that we looked at earlier, has to make 2 bonds. So there's 2. Well, for that O2 to get 8 electrons around each O, they've already got 4. We need to add in 4 more electrons. And so we get that. So we get the 8 in many different ways. Sometimes you have to double bond, sometimes you have to triple bond. The dot diagrams are actually really easy once you know how to draw the structural diagram. So let's look at N2 again. N2, we had a triple bond and 2 electrons on each side. So to draw that thing with the dots, all I do is replace the lines with 2 dots each. So we have our original 2 dots on each end. Each line gets replaced with 2 dots and we're good to go. In fact, you can really see that each of them has 8 electrons here. If we just put a circle around this to show it, you've got 2, 4, 6, 8 for that guy, and this one again has 2, 4, 6, 8 for that guy. And so the dots are really easy. If you can draw the structural and replace the lines with dots, you're good to go. Another example that we can look at is carbon dioxide. Carbon dioxide has this general structure, and you notice the 4 dots on each O and the double bond in the carbon. We go to convert that one into dots, and I have a C, 2 dots for each line, and then put all the original dots that were in the structure before. And so we get that. So dot diagrams are very easy. It's not real difficult. Once you can do the structural, the dots are nice and easy. The next thing we'll look at are the 3D drawings or the 3D diagrams that we talked about in class. And there's going to be some shapes that you need to know for the test, some bond angles, and things like that. So let's go through each of those. The first that we'll discuss is linear. With linear diagrams, again, an example of this one would be CO2, carbon dioxide. And there we've got a carbon bound to 2 oxygens. Well, linear diagrams are really tough to do in 3D. So normally we just draw them as they are. It's really tough to do a 3D diagram of this thing. One of the things you want to be able to do on the 3D that we added in class today is to put in the dipole arrows. And so remember, the arrows point to the most electronegative element. And you need to know your trends for the periodic table to figure out which is more electronegative. When I look at the table, oxygen is more electronegative than carbon, so the arrows point to oxygen. The head of the arrow is negative, and the tail, because it has a positive end on it, is positive. Okay, and that shows the polarity of this molecule. The bonds in CO2 are polar, but the overall molecule is nonpolar. Each of those dipoles are canceling each other out because they're pulling with equal force in opposite directions, like a tug of war between 2 people who are equally strong. When you look at a linear molecule, if it's got 3 atoms in it, the bond angles are 180. The angles between the bonds are 180. So don't forget that. Linear molecules have that. Some linear molecules like HF, if we draw that Lewis structure, we have this. If we draw the 3D, which can't be 3D because it's linear, we get this. Fluorine is more electronegative based on the trends that we know. So I draw the arrow that way. Fluorine is about twice as electronegative as hydrogen, so you get an uneven pool of these guys. There are no bond angles if there's only two atoms. No bond angles, but it is still considered linear in that case. So you should have that idea down. Okay, the next few that we'll look at are molecules that have 4 branches coming off of them. And those branches could be a lone pair, which are unbonded electrons, or they could be a bonded pair. The 4 branches, there's 3 of them that you need to know. The first is a bent molecule. And so when we look at water, if we draw the Lewis structure for that, we have this and this, and it's got some lone pairs on the central atom. And again, according to valence shell electron pair repulsion theory, this is from notes part 2, these electrons will bend these guys down. And so you get what's called a bent molecule. It's a bent shape. That has angles that are about 105 degrees. Okay, for that one. If I go to draw the 3D for that, remember we use a thicker line to show that hydrogen coming out at us as if it was 3-dimensional, and then you can put a dotted line or a regular line going back the other way, and then I put my 2 lone pairs on there, and that gives it the bent shape and the 105-degree angle. The next is the pyramid shape, and a really good example of this is NH3. We have the normal Lewis structure that looks like this. Remember, hydrogen doesn't have any extra electrons on it, and it has the lone pair at the top. So with a pyramid molecule, we get this shape that looks, kind of like this. With that lone pair at the top. The angles on a pyramid molecule are 107. They're not as deflected because they have an extra atom compared to the bent. So bond angles are 107. This is called a pyramid. NH3 is a good example of that. When you're drawing the 3D model, the only lone pairs you have to show are the ones on the central atom. I know hydrogen doesn't have them, but if it was fluorine, you wouldn't have to put any extra pairs on there. It's just purely showing the structure. The last of the 4 branch molecules is known as tetrahedron, and we're going to use an example of CF4, carbon tetrafluoride. We go to draw the Lewis structure. It looks like this. You've got fluorines all around. You've got lone pairs on the fluorines to get the octet rule satisfied. And we go to do the 3D on this one. And again, we show that thicker line coming out at us with the fluorine there. You can put a dotted line for one of them, it doesn't matter which one. And we get that. Again, on the outside atoms, we don't put any lone pairs, and on this one, carbon doesn't have any lone pairs. All its electrons are tied up in bonds. So what we notice is an angle between these guys of about 109. It's really 109.5, but for our purposes, we'll say 109. And we get that. So this is a tetrahedron shape. It's got 4 elements attached. And that's one way to remember that it's tetrahedron. You've got this F, that's 1, 2, 3, 4, to give us that prefix, which is tetra, which means 4. Okay, so those are tetrahedron molecules. Those are the only 3D shapes you really should know. We're going to skip the trigonal planar for the test, but it's good to kind of introduce it to you guys. So that's drawing Lewis structures, the structural diagrams, the dot diagrams, the 3D diagrams. One thing on this tetrahedron one that you can do is show the arrows again. And if we put those dipole arrows, remember they're going to be pointing to the most electronegative element. Fluorine is the most electronegative on the table. And you'll notice that we've got that there.